So, if you're watching this, this is probably cut into multiple videos now because we are having some technical issues. The live stream seems to be interrupting quite frequently, whether it's my internet is slow right now, the server that I'm using for processing the live stream, this Go Lightstream or YouTube, or one of the many things that could happen in between. So I appreciate this is a little bit annoying right now. I'm going to try to keep pressing on because, amidst all the live streaming issues, I'm also still trying to learn this class. I'm trying to make use of the limited time I have. So I'm going to keep pressing on. I don't know how this is going to look in replay. I don't know how good quality it's going to be. Again, I apologize. There's not too much I can do right now. I'm just going to venture forth. So let's go back. So just to recap where we're at right now, I am re-watching a good chunk of Lecture 8 because I wanted to really understand this kind of quote-unquote brute force method for solving the quantum harmonic oscillator to get a better understanding of it.
Notebook if you're taking notes and get the following. No point in me doing this algebra here, alpha u squared over 2, because actually, it's not all that important, over alpha 1 over u squared plus k minus 1 over alpha squared 1. Over u4, all you get look, this is u squared times psi times these things, 1 plus 2k plus 1 over alpha 1 over u squared. So when u goes to infinity, your solution works because these things are negligible. So you get a number times u squared. That is the equation you're trying to solve up there. And therefore, you get that equation if alpha squared is equal to 1. And that means really that alpha can be plus minus 1. And roughly this solution near infinity, probably there's two solutions. This is a second order differential equation, so even near infinity there should be two solutions. So we expect that as u goes to infinity, psi of u will be some constant a times u to the k times e to the minus u squared over 2. That's for alpha equal minus 1. Plus b u to the k e to the plus u squared over 2. And what is k? It's actually probably, hopefully, are negligible. So you squared 1 over 2. Notebook, if you're taking notes. And get alpha 1 over u squared plus k minus 1 over alpha squared 1 over u to the 4th. That's all you get. But this is, look, this is alpha squared u squared times psi times these things, 1 plus 2k plus 1 over alpha 1 over u squared. So when u goes to infinity, your solution works because these things are new. Number times u squared, that is the equation you're trying to solve up there. And therefore, you get that equation if alpha squared is equal to 1. And that means really that alpha can be plus minus 1. And roughly this solution near infinity, probably there's two solutions. This is a second order differential equation, so even near infinity there should be two solutions. So we expect that as u goes to infinity, psi of u will be some constant a times u to the k times e to the minus u squared over 2, that's for alpha equal minus 1, plus b u to the k e to the plus u squared over 2. And what is k? Well, we don't know what is k. It seems to work for all k. That may seem a little confusing now, but don't worry. We'll see other things happening here very soon. So look at what has happened. We've identified that most likely your wave function is going to look like this at infinity. So we're going to want this part not to be present. So presumably we're going to want a solution that just has this, because this is normalizable. The integral of any power times a Gaussian is convergent. So this can be normal. The Gaussian falls so and grow big, it's impossible to compensate the Gaussian. So for this, but we want to translate what we've learned into some technical advantage in solving the differential equation, because after all, we wanted insight how it looks far away, but we want to solve the differential equation. So how can we use this insight we now have to simplify the solution of the differential equation? The idea is to change variables a little bit. So write psi of u to be equal to h of u, that's times e to the minus u squared over 2. Now you can say, why, what are you doing? Are you making an approximation now that this is what is going to look far away? Or what are you putting there? And I'm not making any approximation. I'm just saying whatever psi is, it can always be written in this way. Why? Because if you have a psi of u, you can write it as psi of u over e to the minus u squared over 2 times e to the u minus u squared over 2. Very trivially, this can always be done as long as we say that h is arbitrary. There's nothing, no constraint here. I have not assumed anything, nothing. I'm just hoping that I have a differential. Equation for psi, that because this is a very clever factor, the differential equation for h will be simpler. Because part of the dependence, it has been taken over. So maybe h, for example, could be now a polynomial solution because this part has been taken care of. So the hope is that by writing this equation for, it will become an equation for h of, and that equation will be, so will it be simpler? Well, here again, this is not difficult. You're supposed to plug into equation. Plug into one. I won't do it. It's 3 lines of algebra to plug into one and calculate the equation for h of u. You should do it. It's the kind of thing that you do it. And so please do it. It's 3-4 lines. It's not long. But I'll just write the answer. So by the time you substitute, of course, the e to the minus u squared over 2 is going to cancel from everywhere. It's very easy here. You just need to take 2 derivatives, so it becomes a second-order differential equation. And indeed, it becomes a tractable differential equation. The second h, the u squared minus 2u, the h du, plus e minus 1, h equals 0. Okay, that is our equation now. So now we face the problem of finally solving this equation. So before we start, maybe there's some questions of what we've done so far. Let's see, any questions? Yes.
You have right there, the way this equation is linear, so if we just like, say we e is minus u squared over 2, and then you stuck in that u to the k.
I'm sorry, it's here, this thing?
Yeah. You didn't just power series what's going on at 0 with those u to k terms and sum up a bunch of them?
No. This is the behavior as u goes to infinity. So I actually don't know that the function near 0 is going to behave like u to the k. We really don't know. Yeah, it suggests to you that maybe the solution is going to be near 0 u to the k times some polynomial or something like that, but it's not that, because this analysis was just done at infinity. So we really have no information still what's going on near 0. Other questions? Yes.
So is k some arbitrary number or is it an integer?
At this moment, actually, it doesn't matter, is it right? So, doesn't matter. The analysis that we did here suggested could be anything. That's why I just didn't put it into h of u. I didn't put it because it would be strange to put here a u to the k. I wouldn't know what to make of it. So at this moment, the let's solve this equation. Well, it's not a trivial equation again, but it can be solved by polynomials, and we'll see that. But the way we solve this equation is by a power series expansion. Now, you could do it by hand first, and I did it when I was preparing the lecture yesterday. I said, I'm going to just write H equals H of U equal a constant A0 plus A1U plus A2U squared plus A3U cubed. And I plugged it in here. And I just did the first few terms and tried to see what happened. And I found, after a little thinking, that A2 is determined by A0, and the A3 is determined by A1. Once you substitute, it's not obvious when you look at this, but that happens. So, when you face a problem like that, don't go high power to begin with. Just try a simple series and see what happens, and you see it.
So maybe let's try that and see if we can get the kind of results that he's getting from here. So if we put this in with just the first few terms, well, what would H prime of U is going to be equal to A1 plus 2A2 plus 3A3 squared. Oh, sorry. Oops. 2A2 U 3A3 U squared plus 4A4 3, and then H double prime of U is going to be equal to 2A2 3A3 U oops, no. 6 A3 U plus 8 plus this dot plus dot. And then if we tried this, we would have 2A2 plus 6A3 plus A4 squared plus dot, and then minus 2U U A1U 2A squared plus 3A3 cubed plus dot plus and then this is there's the H, which is going to just be A0 plus A1U A2U squared. And what he's saying is that there's a dependence so which ones are all the same order, I guess, is what's being asked here. So we can see that these ones all like to U and U squared Okay, so that's what he was saying, and I think I have shown that. So let's keep going.
Little pattern, and then you can do a more sophisticated. Be the more sophisticated zero to infinity.
All right, and then let's keep going.
AJ, U to the J.
So H of U is equal to
Then, if you take a derivative, because we're going to need the derivative, dH du would be the sum from A to infinity
J times AJ U to the J minus 1, right?
J times AJ U to the J minus 1.
And then we'll have the D H over D U squared is equal to the same thing. This time it's going to be J times J minus 1 AJ U to the J is 2.
You would say that doesn't look very good because for J equals 0, you have 1 over U. That's crazy. But indeed, for J equals 0, the J here multiplied. So this is okay. Now, the term that we actually need is minus 2U dH du. So here, minus 2U dH du would.
So from H over du minus 2U dH du multiply by 2U, and we're going to get j. We just have this 2 over here.
Be equal to the sum from j equals 0 to infinity, and we'll have minus 2 j aj u to the j. The u makes this j minus 1j, and the constant went there. So here is so far h. Here is this other term that we're going to need for the differential equation. And then there's the last term that we're going to need for the differential equation. So I'm going to go here. So what do we get for this last term? We'll have to take a second derivative. So we'll take h prime was there, so this second h du squared will be the sum from j equals 0 of j times j minus 1 aj u to the j minus 2. Now, you have to rewrite this in order to make it tractable. You want everything to have like u to the j's. You don't want actually to have u to the j minus 2. So the first thing that you notice is that this sum actually begins with
everything in terms of u to the j, not u to the j minus 4.
Because for 0 and 1 it vanishes, so I can write j times j minus 1 j u to the j minus 2. And then let j plus 2, and if j is, look, j begins with 2 in this sum. So if j is j prime plus 2, j prime will be 0. So we've shifted the sum. So it's j prime equals 0 to infinity. And whenever I have a j, I must put j prime plus 2. So j prime plus 2, j prime plus 1, a j prime plus 2, u to the j prime. Wherever I had j, I put j prime plus 2. And finally, you say j or j prime is the same name, so let's call it j. J equals 0, j plus 2, j plus 1, a j plus 2, uj. Okay. So we go to series expansion of everything, so we just plug into the differential equation. So where is the differential equation? It's here. So I'll plug it in. Let's see what we get. We'll get sum from j equals 0 to infinity. The second derivative is here. J times j plus 2 times j plus 1 times j plus 1, a j plus 2, uj, so I'll put it here, uj. Good, that's the second derivative term. Now this one, It's easy. Minus 2j aj, and the uj is there. So minus 2j aj. Last term is just e minus 1. Because it's the function, this j as well. That's h. And look, this whole thing must be 0. So what you learn is that this coefficient value of j, now here, j plus 2, that's j plus 1, aj plus 2, minus 2j minus uj. I think I got it right. This is the same sum. And now, okay, it's a lot of work, but be 0. So as of aj, what I had told you, that you cannot, a2 seems to be determined by a, seems to be determined by a2. So this is saying that a plus 2, 2j plus 2 a very nice recursion relation. It will determine for you 2, a4, a6, a8, all the even ones. If you put a value for a, it will determine for your solution is 0. It's 2 numbers.